Hello students, welcome for this session of your next crash course class. This is for physics and today's topic is work energy and power. Myself Puneet Kathuria, your physics faculty at Aakash. So let's start the topic work energy and power. Now before we start work energy and power, we need to understand the scalar product. So this is scalar product of two vectors. This is also known as your dot product. So let's suppose we have two vectors. This may be vector A and this may be vector B. They are inclined at an angle theta. Now, if I ask you to draw the projection of A along B, so this we can do it as A cos theta and the other perpendicular component is A of sin theta. So when I say what is the projection of A along B, vector B, and this is A of cos theta. So A of cos theta, projection of A along B is A cos theta and B. So we can write it as AB cos theta. And this is what you define it as or understood it as A dot B as the dot product or the scalar product. This is dot product, so we put it like this, AB cos theta, where A is magnitude of A, B is magnitude of B, and theta is your angle between A and B. So this is the physical meaning of your dot product. So that means when you are defining projection of one vector along the other vector, that is called dot product. So any doubt from this part? Any doubt? Okay. So A dot B, we put it as AB cos theta. Now if theta is 0 degree, we know cos 0 is 1, so this A dot B becomes AB only, and when theta is 90 degree, so cos 90 is 0, so your dot product would be 0. And this is how when you have 180 degree, so we know cos 180 is minus 1, so this A dot B can be written as minus AB. Got it? Now if I define I dot I, so we know I is a unit vector along x-axis. So if I say I dot I, so that we put it as magnitude of this, the other vector is also I, and this is cos 0, so we put it as 1 1 and this becomes 1 only. Similarly J dot J is 1 and K dot K is also 1. Whereas if I define I dot J, so that means I J and angle between I and J, because they are perpendicular to each other, so that means cos 90, which is 0, So that becomes 0. Similarly, j dot k becomes 0 and I dot k is also 0. So this is dot product. Now let's attempt one or two numericals based on this. So first we will put a general vector A as ax I cap, ay j cap plus az k cap, and vector B can also be written as bx I cap, by j cap, and this is bz k cap. So when you define A dot B, ultimately you end up with ax bx plus ay by plus az bz. Got it? So let's put it in one numerical form. If I say this is I plus j plus k, and vector B can be written as, so let's take this one as an example. So what is A dot B? So when you define A dot B, so what is Ax? So Ax is 1. What is Bx? Bx is 2 plus Ay is 1, By is minus 1, Az is 1 and Bz is minus 1. So 2 and minus 2 gives you 0. And we know if A dot B is 0, so it means it's AB cos theta is 0, where A is a non-zero vector. So let's define the magnitude of A. So magnitude of A is root 3. Magnitude of B is 2 square 4, 4 plus 1. This is root 6. So as you can see, A is non-zero, B is non-zero. So it's only cos theta. So theta is 90 degree. So it means for this pair of vectors, the angle between A and B is 90 degree. So they are perpendicular to each other. Got it? Any doubt? So Bharat Kaushik has just joined. Good, Bharat. Very good. Welcome to this class. So any doubt from this part? Shall we move? Now let's pick one more numerical we have. Now let's suppose we have vector A as I cap plus j cap plus k cap and vector B as I cap minus j cap minus k cap. Got it? So if I ask you to define projection of vector A along vector B. So this is my first part. Or you may be asked, angle between two vectors A and B. So it means here we have to find out the theta. Now we know A dot B is your AB cos theta. So what is this A dot B? This is AX BX, AY BY plus AZ BZ, which is AB cos theta. So what is AX? So this is 1, BX is also 1, so that makes it 1. AY makes it minus 1 and this also makes it minus 1. So we have to find out, if I have to find out theta, so let's define cos theta. So magnitude of A, so this is 1 square plus 1 square plus 1 square, the whole under the root. So this is root 3 and this is also 1 square minus 1 square minus 1 whole square. So that also gives you root 3. So here it becomes minus 1 by 3 as cos theta. So theta can also be written as cos inverse of minus 1 by 3, which is in the second quadrant. So this is for your cos theta. So that defines the angle between these two vectors. So that was cos theta. Now we have to find out another question, that is projection of A along B. So as we understood projection of A along B, so that we have defined it as A cos theta. So it means we have to find out A cos theta. So what you do is you just leave A cos theta and you divide this part, which was giving you minus 1, and because we have to find out A cos theta, so that means minus 1 by, and the magnitude of B was root 3. So this is the projection of vector A along B. So these are the two standard questions which you may be asked from this section. And ये dot product करना क्यों ज़रूरी है बच्चों? Because we have a chapter that is basically defining your dot product only. So if you have any doubt from this part, first you can clear your doubt. If you have any doubt. So let's move to one more numerical we have. So let's suppose you have two vectors whose magnitudes are given to you as maybe 3 Newton and you may have 4 Newton only. You got it or not? And their scalar product, which is let's suppose we put it as maybe 6 Newton. Then we have to find out angle between A and B. So we know A dot B, which we can write down as AB cos theta. So this scalar product is 6, magnitude of A is 3, magnitude of B is 4. So that makes cos theta as 1 by 2. And you know cos theta 1 by 2 means theta is 60 degree, because cos 60 is 1 by 2. So these are the prime numericals you have which can be asked from this part. So if you are done with this, or if you have understood it, let me move to the next section. So shall we move? Fine. Now let's define the word called work. So work done. So it says work is said to be done if body gets displaced in the direction of applied force, or it may be understood as product of force in the direction of displacement and displacement itself. Got it? So let's suppose if you have a body and you apply force at an angle theta with respect to this horizontal, and if you just split this force into two components, so this is F cos theta, and because of this body gets displaced by value d, then work done is product of force along the direction of the displacement or in the direction of the displacement into displacement. So we call it as Fd cos theta, or this is F dot. So work done is a dot product of force and the displacement vector. So this is a scalar physical quantity and work done in terms of SI units. So force is in Newton and this is in meters, so joule. So in SI system we have joule as the SI unit, and in the CGS system we have ergs. So we know 1 joule is equal to 10 raised to the power 7 ergs. So that is the SI unit of your work done. Any doubt from this part? So work done is Fd cos theta, or this is F dot d. So because work done is a scalar quantity and this is defined as a dot product, so that is why we attempted dot product first. So now we have understood the dot product and we have just understood the definition of your work done also. Any doubt? Any doubt you have from this part? So if you have any doubt, please. Fine. So based on again theta, if theta is 0 degree, work done is F into d only, because cos 0 is 1, and if theta is your acute angle, then work done is basically, because cos theta is positive, so that means work done is positive. You got it or not? So let's understand few definitions of your positive work done. So let's suppose if you have a body and you just apply external force and body gets displaced in the direction of the force, then work done by applied force is positive. Got it or not? Let's suppose you have a body and its weight is acting downward, so you allow this body to fall freely under the effect of gravity. So work done by force of gravity in this situation, when you allow this body to move downward under the effect of gravity, and that means work done by the force of gravity is positive. Got it? Then we have, if theta is 90 degree, then work done is 0. So let's take few examples. So let's suppose we talk about uniform circular motion. So in case of uniform circular motion, so we know this body is moving like this, so its velocity vector is like this, its displacement vector is also in this direction, whereas the centripetal force is towards the center, and that means it is always normal to the displacement vector. So in this situation also the work done by centripetal force is also 0. Got it? Now let's take one more example where you have a pendulum. You allow this pendulum to come to its mean position like this. So let's suppose this is its weight, and if it's displaced by this angular position theta, then this is mg cos theta, this is mg sin theta, and this is the tension. So if I say work done by tension when you allow this bob to come to its equilibrium position. So as you can see, this displacement vector is again normal to the tension. So work done by this tension is also 0. And this work done by mg cos theta, if you can see this mg cos theta and displacement, they are still perpendicular to each other. So work done by mg cos theta is still 0. And if I say work done by mg sin theta, so mg sin theta is basically responsible for this displacement. So this is along. So F into displacement, that is r or maybe d, whatever it is, and this is cos 0. So this work done is there, cos 0 is 1. So in the same situation आपको किसका वर्क डन, किस फोर्स के वर्क डन की बात की जा रही है, दैट इज मोर इम्पॉर्टेंट. सो यू हैव टू बी वेरी पर्टिकुलर कि हम किसके वर्क डन की बात कर रहे हैं, विच फोर्स वी आर टॉकिंग अबाउट एग्जैक्टली. सो दैट डिफाइंस द नेट वर्क डन. Got it or not? So these are the few examples of your 0 work done. Then we have theta as 180 degree. So we know this is cos 180, which is minus 1. So that gives you minus fs. So s is the displacement. So this is your negative work done. And if theta is your obtuse rather, so in that situation also your work done would be negative. So this is, now let's consider a few examples. So let's suppose the same situation, we have a body, it's acted by this gravitational force downward. So if you take this body in the upward direction, so work done by force of gravity when you are moving or when you are taking your body in the upward direction. So as you can see, displacement vector is in the opposite to the force, which is force of gravity. So that means this work done is negative. Got it? So let's take one more example. Let's suppose we have a spring and you stretch the spring, right? So work done by the stretching force, because displacement is also in the same direction. So the spring gets elongated. So this is the displacement. So work done would be positive when you are talking about work done by the stretching force, whereas the restoring force is opposite. So the same work done by restoring force, and that is negative. So this is how we'll be calculating the work done. Similarly, let's suppose if you allow this body to move on this surface and this is the applied force and the body is moving on this frictional surface, whereas force of friction is acting opposite to this motion. So work done by applied force is positive, whereas work done by force of friction is negative. And if I have to find out the net work done, so that means F applied minus force of friction is the net force multiplied by the displacement of the body. That would define the net work done. So Bharat, Kaushik, good. So now any doubt you have from any of the part? If you have any doubt, please do confirm. Sure? So shall we move? Now, so when you write down F is equal to Fs cos theta, where F is the force and S is the displacement and theta is the angle between force and the displacement. So here F is your assumed to be a constant force. Got it? Now let's suppose एक numerical attempt कर रहे हैं. Let's take the value of F as 2I cap plus J cap minus K cap, and this is in newtons. अगर आप एक फोर्स लगाते हैं एंड बॉडी का जो इनिशियल पोजीशन वेक्टर है दैट इज एट I cap plus J cap plus K cap meters. Got it? And because of this force, आपने एक बॉडी को फोर्स लगाया which is at position vector R1 and body gets displaced to a new position vector maybe R2, and this R2 is 2I cap plus 2J cap plus 3K cap, let's suppose, and this is in meters. So आप एक बॉडी के ऊपर फोर्स लगा रहे हैं and this is the numerical value, this is the vector I mean like expression of the force. बॉडी R1 से R2 पर आ जाती है. So how you will calculate the work done? So this is work done is basically force dot displacement vector. So now we are representing displacement vector as R2 minus R1. So when you define the difference, so this is delta R. So now let's define the dot product. So this is 2I cap plus J cap minus K cap dot I cap plus J cap plus 2K cap. Got it? Now this is simply a dot product now. So how we'll define 2 dot 1, so that gives you 1, sorry this 2 and this is 1 1 gives you 1, minus 1 and 2 gives you minus 2. So this goes, so this is 1 and joule. So the work done by this or in this situation comes out to be 1 joule. So this is how you'll be calculating if this kind of question is being asked. So any doubt from this part? यहाँ पे कोई डाउट है बच्चों, आप पूछ सकते हैं. Yes, I am waiting. Shall we? Now the next is, so अभी हमने जो किया उसमें Fs cos थीटा, जिसमें F आपकी एक कांस्टेंट फोर्स मानी गई है because the expression clearly says, but what happens when you have a variable force? So now we'll be doing work done by वेरिएबल फोर्स। अब सबसे पहले एक क्वेश्चन आता है कि हाउ यू विल गेट टू नो कि फोर्स वेरिएबल है, आपको पता कैसे लगेगा? सो दैट इज द बेस्ट पार्ट। सो फोर्स वेरिएबल है, सो लेट्स टेक वन एग्जांपल डायरेक्टली इन द फॉर्म ऑफ अ numerical. So let's suppose if I say your force is given by x square plus x plus 1 Newton. अब आप देख सकते हैं फोर्स इज अ फंक्शन ऑफ x, x इज अ पोजिशन कोऑर्डिनेट। इसका मतलब अगर मेरी फोर्स x के ऊपर डिपेंड कर रही है, इट मीन्स फोर्स इज अ फंक्शन ऑफ x where x is a variable component, so it means मेरी force vary कर रही है। Now I have to find out work done in taking a body from maybe x equal to 0 to a position x equal to 1 meter, let's suppose. So in this situation x आपका वेरी कर रहा है, हर पॉइंट पे फोर्स वेरी कर रही है, सो दिस इज अ वेरिएबल फोर्स। और जब भी हमारे पास वेरिएबल फोर्स का कॉन्सेप्ट रहता है, वी हैव टू गो बाय द इंटीग्रल मेथड। सो दैट सेज स्मॉल वर्क डन इज गिवन बाय f इंटू डी एक्स, एंड वर्क डन बीइंग अ स्केलर क्वांटिटी, तो हमें टोटल वर्क डन के लिए इस एक्सप्रेशन को इंटीग्रेट करना पड़ेगा, एंड फ्रॉम पोजिशन x0 टू x1। So this becomes a simple question. यहाँ पे हमने कॉन्सेप्ट को सीख लिया। If force involved is a variable force, then we have to go by the integral method. So let's put the value. So x square into dx plus x into dx plus 1 into dx. Got it? So that gives you what? X cube by 3 plus x square by 2 plus x. Now we have to put the limits. So when you put the limits, so it becomes 1 by 3 plus 1 by 2 plus 1 only, and you take the LCM, that makes 6. So this is 2 plus 3 plus 6, so that means 11 by 6 joule is the work done. Got it or not? Any doubt you have from this part? Sure? अब यहां तो हमें एक इक्वेशन गिवन था। What if this variable force is given to us maybe in the form of a graph? So let's pick one more numerical where x is in meters and this is in newtons. So now we have force versus displacement graph. Got it? So how you calculate work done? So if I ask you calculate work done from x equal to 0 to simply x equal to 2. So this may be the first part I may be asking. So in the second situation, let's do it from x equal to 0 to 6. So basic concept goes the same because this is a variable force concept. So we'll go by the integral method. So we'll calculate f into dx and we just integrate it maybe from limit 0 to 2. एंड दिस टाइम हमारे पास फोर्स इक्वेशन के फॉर्म में नहीं है गिवन। दिस फोर्स इज गिवन टू यू इन द फॉर्म ऑफ अ ग्राफ। सो वी नो द फिजिकल सिग्निफिकेंस ऑफ दिस इंटीग्रल इज, सो दिस एफ डी एक्स रिप्रेजेंट्स एरिया अंडर द ग्राफ। सो सिंपली इफ यू फाइंड आउट द एरिया ऑफ दिस शेडेड पार्ट, दैट वुड डिफाइन द वर्क डन। सो दिस इज एरिया ऑफ triangle. So So from 0 to 2, so that means half into base into height, so that defines your 10 joule. But when I ask you to find out work done from 0 to 6, so we have to find out this complete area. Got it? And this area is primarily your area of trapezium. कैसे निकालते हैं बच्चों आप area of trapezium? So that means area of trapezium is half into sum of parallel sides. So this side is 6, this side is 2. So sum of parallel side becomes 8 into height, and this, or the gap between these two parallel sides, so which is 10 again. So that makes it 40 joules. So this is how you calculate the work done if force versus displacement graph is given to you or known to us. Any doubt from this part? Good. So Zaikuddin Khaja has given me the right answer. Bharat Kaushik has given me the right answer. Shall we move? Now let's pick one more numerical. Now let's suppose if you have force versus displacement graph like this, got it? Then how you will calculate the work done? So if I ask you to find out work done maybe from x equal to 0 to x equal to 8 meters only. So quite simple, we have just understood. So this work done is primarily f into dx. So now we'll split this part into two parts. So this is one which is giving you positive work done. So this is 0 to 4, then f into dx from 4 to 8. You got it or not? So this is area of the first part, which gives you area of this rectangle. So this is 10 into 4, 40. Whereas in this case, in this situation, this work done is there, but this work done is negative because force is on this side. So this is minus 5 Newton. So area of this rectangle is again 4 into 5, and that gives you minus 20. So if I ask you the net work done, so work done being a scalar quantity, we simply add the positive work done and the negative work done. So that gives you 20, and unit wise this is again the joules. So this is how you'll be calculating the work done using your F versus X, force versus displacement graph or curve you have. So any doubt from this part? Good. So if you have any doubt, you can still confirm your doubt. Now let's pick one more numerical. This time your force is given to you as x I cap plus y g cap in newtons, and you move from one comma one to if it is like this, so let me just keep it in 2D motion only. So this makes it 2 comma 2 meters. Got it? So is this a variable? So when you say work done as F dot dr, So we simply put it like this, x I cap plus y j cap, and this is dx I cap plus dy j cap. And when you define the dot product, so it gives you x into dx, and this gives you y into dy. So you are moving from 1 to 2, and in this situation also you are moving from 1 to 2. So that gives you x square by 2, that gives me y square by 2, and when you put the limits from 1 to 2 in both the situations, so that gives you what? So that gives you 1 by 2, we are taking common for this, so this means 2 square minus 1 square plus 1 by 2. For this part also it is 2 square minus 1 square and that defines 4 minus 1 as 3, so this is 3 by 2 plus 3 by 2, that makes it 3 joules only. Got it or not? So any doubt or anything you would like to ask from this one? So Nishit has also joined. So Nishit, Zaikuddin, Bharat, good, keep it up, good, keep moving. कोई डाउट है तो बच्चों पूछिए. Shall we? Okay, so this was all about your work. So we have just completed the work done part. Now let's start with energy. So how you define energy? It's the same definition which you had been defining since your 4th, 5th, 6th class. So this is basically capacity to do work. Got it or not? So here primarily we'll be dealing with first type of energy, capacity to do work. So here we'll be talking about kinetic energy first. So this is basically energy possessed by a body by virtue of its motion. Got it? So kinetic energy is also in terms of SI unit, so it has joules. In terms of dimensional formula, this is also energy, so energy is ml square T minus 2. So this is same as that of work done. So this is the same concept, and this kinetic energy we know is half mv square, where this v is basically speed. And when you write down half mv square, so this half mv square kinetic energy is a scalar physical quantity. When you say v, v depends on the frame of reference coordinate system. So this kinetic energy depends on frame of reference also, because a body may be defined at rest in one coordinate system or maybe in motion with respect to another coordinate system. So that defines ultimately the speed, and hence finally the kinetic energy will also be depending on the frame of reference we have. Got it or not? Any doubt from this part? Now we know momentum also quantifies the amount of motion we have. So momentum is mass into velocity. So in terms of its magnitude, so we simply put it as mass into its speed. So how kinetic energy half m v square, we put it as m square v square, and this we put it as p square by 2m. So this is the relation you have between the kinetic energy and the momentum. Now we have a very few questions based on these two relations, kinetic energy and momentum. So momentum can also be written as 2m times kinetic energy under the root. So let's pick one numerical. If momentum of a body is doubled, then find percentage change in kinetic energy of the body. So this is quite interesting. अगर हम बॉडी के मोमेंटम को डबल करते हैं तो हमारी बॉडी की नई काइनेटिक एनर्जी क्या होती है, और चेंज इन काइनेटिक एनर्जी या परसेंटेज चेंज इन काइनेटिक एनर्जी. सो ऑल दीज क्वेश्चंस कैन बी आस्क्ड फ्रॉम दिस पार्ट. आप देख सकते हैं मोमेंटम आपने डबल किया है, मास के ऊपर कोई कमेंट नहीं है, सो विल कीप मास एज कांस्टेंट. सो लेट्स सपोज इनिशियल काइनेटिक एनर्जी ऑफ द बॉडी में बी E1 एंड मोमेंटम इज p square by 2m. The final kinetic energy is, अब momentum is p2, which we can write down. So if I simply put it as p, and for the second body momentum को आपने double किया है, so that becomes 4p square and keeping the mass same. So just go and take the ratio. So E2 would be 4 times E1, and percentage change on kinetic energy is E2 minus E1 by E1 into 100, so that makes it 300% only. Got it or not? So any doubt from this part? Shall we move? If momentum of a body is increased by 2%, then find percentage change in kinetic energy. So we know kinetic energy is basically p square by 2m. But now look at this. This momentum is increased by 2% only, matra 2%. So whenever you have change in one of the variables less than 6-7%, right? So probably we'll go by error method. And percentage change in kinetic energy is, so mass, there is no comment, so we'll keep mass as constant, so there is no change in the mass. So it means by error method, so this is 2 times change in momentum, and momentum is increased by this 2% only, so 2 into 2 will make it 4% only. Got it or not? Any doubt? So momentum is increased by 2%, then percentage change in kinetic energy would come out to be 4%. Now we have another numerical. If now kinetic energy is, let's suppose, increased by 100%, then what is the percentage change in momentum of the body. So this is a new question. Then percentage change in momentum. So we know momentum is 2m times kinetic energy. So if this is momentum P1, mass पर कुछ comment नहीं है, and P2 is √2 times m, और kinetic energy is increased by 100%. So पहले kinetic energy आपकी E थी, आपने 100% उसको increase किया, so the new kinetic energy would be 2 times E. Then if you look at this, so how you will find out P2? P2 would be √2 times P1. And how you will calculate the percentage change in momentum? So that is P2 minus P1 by P1 into 100. So that means √2P minus P by P into 100. So P goes, so √2 minus 1, 0.414 into 100. So that makes it 41.4%. So that is the increase in momentum of the body if you increase the kinetic energy by 100%. I am speaking in English. Saran Raj, I think I have hardly used any of the language other than English. So please be focused. So any doubt from this part if you have? So this is all about this part. So how kinetic energy and momentum based questions can be asked. Now we have another concept, stopping distance. So how you will find out questions from this topic? So let's suppose you have a body of mass m initially moving with speed u, and it stops purely because of friction after traveling some distance s, and this is moving with a uniform retardation. You got it or not? Because so body is moving with some initial speed u and it's moving on the frictional surface, and after covering some distance s, it stops. So we know v square minus u square equal to 2as, and this is a retardation motion. So u square by 2a is your stopping distance. Got it? Then what is this retardation is? So we know this is the motion and it's been stopped by friction only, and friction is mu mg. So this retardation is mu g. So u square by 2 mu g is your stopping distance, and the stopping distance is s only. You got it? Now you multiplied with mass, you divided by mass. So let's make a new step. So you multiplied with mass, so this is how, and this is the initial kinetic energy you have. So this is the initial kinetic energy with which your body was moving, and this is mu mg. So this is how you will be finding the stopping distance also. You got it or not? So now if you look at the formula, so you have one formula, you have another formula, you may have third formula. So all these formulas will primarily define the varieties of objective question that can be asked from this section also. So if two bodies are moving with the same kinetic energy but different masses on the same surface having the same mu, got it or not? So let's define one numerical. So stopping distance is basically kinetic energy by mu mg. Got it? So let's suppose you have two bodies. So you have body M1, you have body M2. They are moving with same kinetic energy, right? And mu is also same for both the bodies. So if two bodies of different masses M1 and M2 moving with the same kinetic energy on the same frictional surface having same coefficient of friction, then if I ask you there, compare their stopping distances, got it or not? So as you can see, kinetic energy is same, mu is same, g is also same. So stopping distance in this situation is inversely proportional to its mass. So S1 by S2 is simply M2 by M1. Got it or not? So stopping distances, yes, there is a ratio of stopping distances we can easily find out if we know the masses, and that is inverse of their mass. So that depends inversely on the mass. So a body of heavier mass, mass agar, if mass is more, then stopping distance would be small for this situation. You got it or not? Any doubt from this part now? Fine. So now we'll move to work energy theorem. And work energy theorem is change in kinetic energy of the body is work done by all the forces or work done by net forces, all the net forces, whatever the work done. So you may have more than one force. So what is the net work done by all the forces? So that defines the change in kinetic energy. So this change in kinetic energy is half m v square minus half m u square. So that defines the change in kinetic energy. So this is again one very important area from which you may be asked numericals or maybe conceptual questions based on this. Got it? Now let's pick one numerical which is quite famous in this situation. Let's suppose, keeping the data simple, let's keep mass as 1 kg. So if position of the body is given by this expression. So x is equal to t cube only. Got it or not? So x is a function of time and this is a cubic function of time. So we have to find out work done in maybe, let's suppose, first 2 seconds. So what is the work done in the first 2 seconds we have, right? So we'll go by the same principle, right? Because this is how we'll define the work done using this principle. So let's define the velocity just by differentiating it. So this gives you 3t square. Now to find out initial velocity, it means I have to put t as 0. So this initial velocity, just by putting t 0 in this expression, gives you initial velocity as 0. And what is the final velocity at the end of 2 seconds? So that defines 12 only. And if I apply the concept of change in kinetic energy, that is basically defining the concept of work done. Got it? Then half m v square minus u square. Change in kinetic energy defines the work done by the body in this situation in first 2 seconds. So this is how you will be finding. So put the value of mass as 1, v square. So what is v? V is 12, 12 square minus u is 0. So 12 square becomes 144. So this is primarily 144 by 2 and that defines 72 joules only. So this is the work done in the first 2 seconds if position of the body varies as per this expression, as per this equation. Any doubt from this part? Any doubt? Okay. Now let's pick one more numerical. Let's suppose you may have a bullet of mass 10 grams, got it, moving with speed 100 meter per second, enters into this wooden block and after traveling it comes out with 50 meter per second. So piercing through this block, the bullet is coming out finally with speed 50 meter per second. So we have to find out work done by resistive force. And that resistive force is purely offered by this block and it has slowed down. So we know the change in kinetic energy half m v square minus u square defines primarily the work done. So if this work done comes out to be, this part is negative, so it means it is the work done by the resistive force. So this is half, mass is 10 grams, so that means 10 by 1000, so that keeps you in SI system. V, final velocity is 2500 minus u square is, you got it or not? So that means half into 1 by 100 and this 10,000 minus this gives you 7500. So this goes with this and this goes with this, so that makes it 37.5. Definitely this is a negative sign, so negative sign indicates it's a work done by the, work done by what? Work done by the resistive force. Got it or not? So we have just attempted work energy theorem and 2 numericals based on your work energy theorem we have. So good. Okay, so shall we move? Now we have concept of potential energy. So this is primarily the energy possessed by a body by virtue of its position or configuration. Configuration means system. So we have gravitational potential energy, we have elastic potential energy, then we have electrostatic potential energy. So this will be dealing in plus one, and this is purely a part of your electrostatic part, involves the charges at rest. So this is a part of your plus 2. So we'll be focusing primarily on these two. So gravitational potential energy and elastic potential energy. You got it? So we have gravitational potential energy. Now let's build up the concept as quickly as we can. So this is a body of mass m it's acted upon by force, and you take this body against the force of gravity to a height h. So work done by force of gravity. So this is mgh cos of 180, because as we have just discussed, this force is there and this theta is 180. So this negative work done by force of gravity gives you mgh as increase in potential energy. So this gives you change in potential energy, and this is increase in potential energy. So this is positive. And if you just throw this body with some speed u, finally it ends up at its maximum height with final speed 0. So that gives you decrease in potential, this decrease in kinetic energy. So this decrease means we have a negative sign. And the best part is, at this point, the energy stored by virtue of it, this extra energy stored by virtue of its position, that means this is energy stored as increase in potential energy, and this is mgh. And you know, this energy stored is recoverable. So if this energy stored is this potential energy, the potential energy stored in the body by virtue of its position now, h, is this recoverable. So when you allow this body to come down, so work done when it is moving down by gravity is positive, and this positive is mgh. So whereas we had negative work done when it was moving up, so work done around the trip is what? 0. So this gravitational force is a conservative force. So it means got it? So what do you mean by conservative force? So force is said to be conservative if work done by that force, that conservative force, depends only on initial and final position, and this is rather work done is, I'm talking about work done, mind it, work done is independent of path followed. The negative work done gives you increase in potential energy or maybe decrease in kinetic energy. Got it? Whereas positive work done gives you decrease in potential energy and increase in kinetic energy. And work done round the trip is 0. So all these are the properties we have just discussed, so that qualifies the force as conservative force. So there is another property. This conservative force is negative of potential energy gradient. So conservative force is negative of potential energy gradient we have. Got it or not? So these are the properties of your conservative force, whereas in case of non-conservative force, which primarily deals with your friction, and all the resistive forces are non-conservative forces. So work done is wasted as heat, or that energy is not stored. So there is no question of recovering that, and this is how you'll be defining the conservative force. It means the concept of potential energy defined only for conservative forces or fields. It means potential energy is not defined for non-conservative fields or non-conservative forces we have. So example of conservative forces: elastic force, gravitational force, electrostatic force. These all are conservative forces, whereas non-conservative forces are dissipative forces like your resistive force, frictional force, viscous force. All these are non-conservative forces. Got it or not? Any doubt? Then we have concept of equilibrium. So what do you mean by equilibrium? Equilibrium means the net force acting on the system is zero. So here we are talking about conservative force. So du by dx is your conservative force. So that means the very first condition we have, that is du by dx is 0. And based on this, we define three types of equilibrium. One is stable equilibrium. So as you have equilibrium, so force is 0, it means du by dx is 0. And here, if you draw, or let me draw on this side. So if you draw your potential energy with respect to position, so this is how the curve looks like, and the concept of potential energy is minimum in this, and for the potential energy to be minimum, your second order derivative is what? Is greater than 0. So if body is somewhere here, and if you disturb the body from this stable equilibrium position, right? So if you just disturb it, then restoring force will come into play, and that will try to bring the particle back to its stable equilibrium position. So restoring force will come into play. So F is equal to minus kx will be there. Then we have second type, that means we have unstable equilibrium. So because this equilibrium is still there, du by dx is 0, and if you draw your potential energy with respect to x, so this is like this. So this is the position of unstable equilibrium. So second order derivative is less than 0, and potential energy has a maximum value. Got it? And there is no restoring force. So no question of restoring force. The moment you disturb the body from its unstable equilibrium position, it has a tendency to move along the direction of the force, in the direction of the force, and there is no restoring force, so body will not regain its stable equilibrium or unstable equilibrium position in this situation. And in the third situation, you have a neutral equilibrium. So in case of neutral equilibrium, du by dx is 0, and as the name suggests, this potential energy with respect to x, so that remains constant. So second order derivative of this potential energy is still be 0, and if you displace the body, so body gets displaced, but there is no restoring force. So these are the interesting situations for your stable, unstable and neutral equilibrium. Now let's pick numerical. Let's suppose if I keep mass as 1 kg and potential energy as x square by 2 minus x. If I say total energy of the body is 2 joules, what is the maximum speed of the particle? So this is a very important question, and this is one of the important formats we have for the NEET. So this is like a PYQ. So this is the question. Now we know if I have to define total energy, so that means its kinetic energy and its potential energy, and because I have to define the maximum speed, this means potential energy has to be minimum. So what is this minimum potential energy? Because this total energy is given to us or known to us as 2 only. So let's define U minimum. So du by dx, so that defines 1 by 2, 2x minus 1. So for that, for the minimum part, this part has to be equal to 0, so x equal to 1. Let's check the second order derivative whether it satisfies the condition for the minima or not. So it means x minus 1, and when you define it again, so it gives you 1. So 1 means it's greater than 0. It means potential energy is minimum, and that minimum happens at x equal to 1. So let's define the minimum potential energy, and that means x square by 2 minus x. So we'll keep x as 1. So this means 1 by 2 minus 1, that gives you minus 1 by 2. So 2 is equal to half mass, we'll keeping it as 1. V maximum, we have to find it out, and U minimum is minus 1 by 2. So that means 2 plus 1 by 2 is equal to 1 by 2 V maximum square. So this makes it 5 by 2. And the maximum speed comes out to be root 5 meter per second. In this situation. So this is a very important NEET question which have been asked. Dheeraj, please repeat. Okay, Dheeraj, just pay attention. Mass is known to us as 1 kg, and expression of potential energy, how the potential energy in this situation varies. So this is the equation. If total energy given to you for this particle is 2 joules, then we have to find out the maximum speed. We know as per your conservation of energy, total energy, mechanical energy is kinetic energy plus potential energy. Potential energy is minimum, then only we have the maximum speed or the maximum kinetic energy. So for the minimum part, we just did the derivative part of du by dx as 0. So that makes x as 1. So second order derivative clearly verifies the potential energy is minimum. And how you find out the minimum potential energy? Just put the value of x as 1, that defines minus 1 by 2. Put the values, and that defines the maximum speed as root 5 meter per second. Any doubt? Sure. Let's put one more numerical. So let's suppose this is force. Got it? And these are the 3 positions. So let's suppose this is P, this is Q, this is R, and this is X. Then I have to ask position of equilibrium. This is the first question. Then position of stable equilibrium. So this is again one of the important conceptual case we have. So how you will find out? So for position of equilibrium, we know equilibrium means force has to be 0. So force is 0. If you look at the graph, so these are the only 2 positions where force is 0. So the answer for this part is Q and R. But when you ask about the stable equilibrium, this is not the position, because P point has the maximum force. Look at the graph. So P is not there. Then we have to find out the stable equilibrium. So out of these two, we know for stable equilibrium, we have F is equal to minus Kx. So it means with the increase in value of x, F has to decrease. So when you move from this to you increase the value of x, the value of force decreases. So this is the position of the stable equilibrium. In this situation, when you increase the value of x, force increases. So this is not the position of your stable equilibrium. You got it? Then the next part we have is your power. So which is defined as rate of doing work. So work done per unit time, so joule per second, and that defines the SI unit as watt. The other unit is horsepower, which is 746 watt only. Got it or not? So we have two types of power. We have average power, that defines the total work done upon total time taken. Then we have instantaneous power. So instantaneous power is defined as F dot V only. Got it? So let's pick a numerical. Let's suppose you have a body maybe of mass 40 kg. You lift it to a height of 100 meters. Got it? And you take time 40 seconds. And with the machine with which you are taking this body up, so machine has an efficiency of just 80%. So you are lifting it with the help of an external machine. Then find input power supplied to the machine to do this work. So we know efficiency is basically output power by input power. So output power is mgh per unit time, and if I have to find out input power, so we'll divide it by efficiency. That makes it like this. So what is this? M is 40, yes, G is 10, H is 100, time is 40 seconds only, and this is 80 and this is 100. So this makes, and this is 1.25 rather, and we'll keep this 100 intact. We'll just simply kill it with this. So 100 and this 0, so that makes it 1.25 into 10 raised to power 3, or 1.25 in terms of wattage. We'll simply put it as kilowatt. So this is the input power supplied. Got it? Now the next important article from this part is your collision. So two bodies, if they interact, so that they interact for a very short duration of time, and during that short duration of time you have a change or exchange of momenta between these two, even without physical contact, that is called collision. So for particles to be in colliding state, there is no physical contact which is mandatory for the collision to happen. So it may happen even if they are interacting because of internal forces. So because of this nature, we have elastic collision and inelastic collision. Got it? So in elastic collision, your linear momentum is conserved, and even in inelastic collision, your linear momentum is conserved. Here total energy is conserved. Here also total energy is conserved. Here kinetic energy initial is equal to kinetic energy final. So kinetic energy is conserved. Here kinetic energy is not conserved. It means there is loss of kinetic energy, and that loss may be in the form of heat, sound, light, or maybe in all the three forms. Here also very important point to be noted, the kinetic energy of the system before the collision and after the collision is same, but kinetic energy during collision, so that during collision is delta T is very small. So even in this interval, when these two bodies are interacting, colliding, the kinetic energy is not conserved, because during that period they are exchanging the momenta with each other. So that means kinetic energy is conserved before and after, but not during the collision part. You got it? Then we have another term that is called coefficient of restitution, E, which is defined as ratio of velocity of separation to velocity of approach. Got it? So this is coefficient of restitution for perfectly elastic collision, coefficient of restitution is 1. For perfectly inelastic collision, coefficient of restitution is 0, and for real life collisions, coefficient of restitution lies between 0 to 1. Got it? Then we have you may have elastic collision in one dimension. So you have M1 may be moving with U1, you may have M2 moving with speed U2. So they collide, and after collision they move with speed V1 and V2. You got it? So coefficient of restitution is velocity of separation by velocity of approach. This is the one. Then conservation of linear momentum, that defines m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Then we have another concept that gives you conservation of kinetic energy. So half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So these are the three prime equations we have, and based on this their final velocities after collision can be written as m1 minus m2 into u1 plus 2 m2 u2 by m1 plus m2. Similarly, for the V2, final velocity of the second part, m2 minus m1 into u2 plus 2 times m1 u1 by m1 plus m2. You got it? So we can make use of all these formulas, and I would like to teach you very fine numerical before I close my session, and this involves your very important numerical. So let's suppose you have one body, it's moving with speed u, strikes the surface at an angle alpha. It moves with speed v, maybe at an angle beta. Got it? Then if I just define this part and this part, the components of the initial speed. So if this is alpha, this is alpha, so this is u of cos alpha and this is u of sin alpha. For this part, if I define this one, so this is beta, v of cos beta and this is v of sin beta. Got it? Now, the component which is along the surface will not get altered. So u sin alpha can be written as v sin beta. This is the first equation. Then this part v cos beta is e times, where e is the coefficient of restitution. So this is e times this perpendicular component is u cos alpha. Just take the ratio and what you will have, tan alpha by e is equal to tan beta. So this is the third prime equation. So based on all the three equations, you have varieties of conceptual and numerical problems. Then squaring and adding. So this gives you u square sin square alpha plus e square cos square alpha. U we are taking it common, and on the other side it's v square sin square beta, v square cos square beta, so that gives you v square only. So these are the four prime equations we have, and based on this you may have varieties of numericals that may be asked or maybe a conceptual question. So time is not permitting to drag it further. So I wish you good luck for your NEET part, and thank you very much for attending this session. So this is all from my side. Thank you very much.